Welcome back. In this lecture, we will compare the energy level of a semiconductor, which we introduced in the previous lecture, against the energy levels that are used in electrochemistry. So we have introduced the electrochemical scale in over the course of many lectures, which is and these energy scales in electrochemistry are represented via the standard reduction potentials. So how do we compare them? And we'll also see why do we need to compare them. So let us step back and look at the energy scales in electrochemical systems, and let's see whether we can interpret in a intuitive manner. Okay, so finally, when you think about electrochemistry, the simplest reason why we want to be thinking about electrochemistry is to do redox reaction. Something is getting oxidized, something is getting reduced, and we want to get a sense for what is getting reduced and what is getting oxidized. So this is the simplest reason for getting into electrochemical systems. So we've already talked a lot about electrochemical reduction potential when we started discussing electrochemical thermodynamics. That is, you should look at the previous lectures, but we'll just try to interpret electrochemical potentials in an intuitive sense. Why I have put within quotes, because these are all deep thermodynamic quantities. Without clarifying how thermodynamics gets in, we are just presenting the electrochemical potential tables. What do you mean by thermodynamic potential? I'm trying to say that these are not mechanical potentials. When you say something is a mechanical potential, that doesn't involve temperature. As soon as temperature gets involved, the potentials are thermodynamic potentials. Again, to make sense of all these things, you have to take a class in statistical mechanics. All right, let's just stick to electrochemical system. Let's make sense. So these elements, let's say lithium, has a negative, fairly high, very negative reduction potential. Whereas, let's say Au3 plus has very positive reduction potential, or it's hard to make sense of gold in a straightforward manner. But what you know, just from your high school intuition, is chlorine is an electronegative element, oxygen is an electronegative element. So they have positive reduction potentials, whereas very electropositive elements, let's say like lithium or aluminum, so this reduction is very negative. So what does it really mean? So when you say something has positive reduction potential, that means that particular element can easily be reduced. That is chlorine, diatomic chlorine, that is chlorine gas, will very easily take up electrons and become Cl minus. Likewise, oxygen can take up electrons and protons, can become water, or let's say gold. You just from your chemical intuition from your high school, you would know that it's hard to ionize gold. So gold is actually a very electronegative element. So if you have Au3 plus, it can very easily get reduced and form Au. So that's what you mean by saying some elements have high reduction potential. Lithium, on the other hand, being very electropositive, it is reducing lithium. That is lithium. When you say lithium, here we're talking about lithium ions. Because lithium is very electropositive, lithium, instead of being in zero state, it will be it would prefer to be in a positive state. So this reduction, that is reduction of lithium cation by an electron from lithium, is not very easy. That's not a favorable process. So it has a negative reduction potential. That means this reduction is not very facile. It's not very easy. Of course, you can also convert this using delta G is equal to minus NFE and make sense of the energies involved in this reduction processes via free energies, right? So when we say delta G is equal to minus NFE, so if you implement that for this particular system, delta G will be very positive. Whereas if you implement delta G is equal to minus NFE for this system, that delta G will be very negative, meaning that this reduction is very favorable. And when you say delta G is unfavorable, this reduction is unfavorable. So this is interpreting the reduction potentials in a simple high school inorganic chemistry sense. So let's again get back to certain other definitions. When we say something is a good oxidant, what do we mean by that? It gets reduced easily, right? So good oxidant, when it tries to oxidize something, that material itself gets reduced easily. That's what you mean by a good oxidant. So the simplest utility of a reduction table, standard reduction tables that are present in electrochemical system is for thinking through this kind of chemistry, right? So more positive potential oxidize those species which have less positive reduction potentials. So let us try to understand this using the reduction potential. So we are talking about redox reaction, right? So when we say more positive, that there is an oxidant and reduction species, reducing species, something is getting oxidized, something is getting reduced. So let us take this pair, redox pair. Let's say take chlorine. Chlorine has a more positive reduction potential. So when you are taking this pair with this pair, because lithium has a less positive reduction potential. So it's very easy to utilize chlorine to oxidize lithium metal. So when lithium is getting oxidized to lithium plus, chlorine is getting reduced to Cl minus. So to see what can be oxidized and what can be reduced, that chemistry of redox chemistry, there is simultaneous reduction and oxidation occurring. To know which is getting reduced, which is getting oxidized, this tables of electrochemical reduction potentials is very useful. While we have talked about oxidation and oxidants, we can equivalently think about reductants. A good reductant is one that is used for reducing something else. So while it is reducing something else, the reductant itself gets oxidized, right? So contrast this definition with this definition, okay? But they are in a way equivalent, right? Here we are thinking through oxidants. Here we are thinking through reductants. So how do we use standard reduction potentials to think through this? So more negative reduction potential will reduce species with less negative reduction potentials, okay? So this is the simplest utility of standard reduction potential tables. So this, you must have seen this from your high school chemistry itself. So let's see how to use these concepts in when we are looking at semiconductor electrochemistry. So the important thing to notice is when we talked about the energy scales in electrochemical systems, that is these energy scales, we talked about this in using the standard hydrogen electrode, right? In a standard hydrogen electrode, there is some reduction that is occurring. That is, protons are getting reduced by electrons to form hydrogen. We assign a value for that reduction potential, that is the capacity of proton to get reduced, we assign the value 0. With respect to that, we talked about some species which can get reduced more easily, and some other species which are harder to reduce. So all this measurements were made against the standard hydrogen electrode, right? That in the previous lectures, we have classified the meaning of standard hydrogen electrode and normal hydrogen electrode. Anyway, that's a detail. We use this electrochemical scale. However, in semiconductor physics or in solid state physics, we talk about work function, right? So in the previous lecture, we had clarified the meaning of work function. We talk about the work required to remove an electron from a solid and placing it in vacuum, right, at infinity, right? So it is a bit abstract because what exactly we mean by placing the electron in infinity or vacuum, that's not a very simple experiment. In my opinion, these are much simpler experiments. How to quantify energy in electrochemical systems is a much more simpler experiment compared to removing an electron and putting the electron in at infinity. In any case, we have defined the work function in the following manner, right? So if the electron is bound to a greater level, that means its binding energy is more negative. In physics, we say when something is more bound in a greater manner, its energy is more negative. Something is more stable, its energy of that system is more negative. So this is the energy scale that is typically used in physics, especially in solid state physics. This is the energy scale that is utilized in electrochemical system. But in photoelectrochemical system or in semiconductor electrochemistry, we have to bring together these two concepts, because the electrode, or in some cases you will be metals, in some cases it'll be semiconductors, and the energies of metals and semiconductors are typically referred to using work function, whereas the redox couples that are present in the electrolyte would be specified using the energy scales that are developed in electrochemical systems. So when there is an electron transfer between the electrode, whose energies are represented in this manner, to a redox couple whose energies are referred in this manner, to see which electron transfer is possible, we have to a way of comparing this against this. So let's start by looking at some data, what is shown here. So first, this is a quantity that is familiar to you. This is the redox potential of standard hydrogen electrode or normal hydrogen electrode that has a value of 0 in the electrochemical scale. There is a way of comparing what is this scale against this scale. We won't elaborate on that, but this scale is related to the electrochemical scale using this equation. We won't go into the basis for this equation. Again, that involves a lot of statistical mechanics. Without going into that, we are just going to mention that there is a way of converting this scale to this scale. How do you intuitively think about this? The way to think about this is, supposing we have a redox couple, that is, the redox couple we are interested is this redox couple. That is, two protons are there in the electrolyte and two electrons are present in the electrode, and hydrogen gas is also present at unit activity in this system. So because the electrons are present in the electrode, supposing we remove that electron that is present in the electrode and ask how much energy has to be utilized for removing that electron from the electrode, that would be about negative 4.44. Okay, so again, let me clarify. So there are many quantities. In the electrochemical sense, we have a redox couple involving protons and hydrogen. And there is a third quantity, which is the electrons. And the electrons are present in a metal electrode, let's say platinum electrode. And if you're asking the question, how much energy is required to remove the electron that is present in platinum, which has been exposed to hydrogen of unit activity and protons of unit activity, that energy would be about negative 4.44, negative 4.44 electron volts. Okay, so that is one way to think about this relationship. But there is it involves a lot more statistical mechanics. Without referring to fundamental statistical mechanics, I've just given you a way to think about this energy against this energy. In addition, there are other quantities. So what are we specifying here? Let's take silicon. 1.1 refers to the band gap of silicon. Let's say 3.2 refers to the band gap of titanium dioxide. Likewise, there are many other semiconductors whose band gaps are specified here. And there is the conduction band and there is valence band of these semiconductors. So when we specify the conduction band position and the valence band edge, the edge of the valence band position against this electrochemical scale, what are we talking about? Again, try to relate to this kind of representation. Whenever we are showing a standard reduction potential, we are thinking about some reduction process, that is a particular species is reduced by an electron. That's what we are talking about. That same ideas, similar ideas are applicable here too. Supposing we are talking about a reduction where the electron is added to the conduction band of silicon or the conduction band of arsenic in gallium arsenide or tellurium in cadmium telluride. So that will involve, we can specify the reduction potential for that reduction process. That is adding an electron to the conduction band or adding an electron to the valence band of a semiconductor. So when we talk about that electrochemistry, okay, so we can talk about the reduction potential for that particular process. That is what is being specified against the reduction potential scale for such processes. That is adding an electron either to the conduction band, that would involve this reduction potential, or if you're adding electron to the, this refers to valence band. If you're adding electron to the conduction band, the reduction potential will be this quantity. When these positions are referred to this scale, the energy that is required to remove an electron from the valence band will be this quantity. The energy that is required to remove an electron from the conduction band will refer to this quantity. Let's take other extreme. Let's take titanium dioxide. If you want to add an electron to the valence band of titanium dioxide, if you ask what is the reduction potential, that would be this quantity somewhere in this region. If you want to add an electron to the conduction band of titanium dioxide, that'll be some quantity here. Then against this scale, if you ask how much energy is needed to remove an electron from the valence band of titanium dioxide, that will be some quantity here. If you ask the question how much energy is required to remove the electron from titanium, the valence conduction band of titanium dioxide, there will be some quantity here. So why is this all required in the first place? So if you remember, when we introduced photoelectrochemical systems, what did we say? In a photoelectrochemical system, the semiconductor absorbs a photon, and when a photon is absorbed, there is an excitation of the electron from the valence band of semiconductor to the conduction band. So this is called an exciton, and whole electron pair is generated. We won't uh, elaborate on band bending here. That will be done in the next class, next lecture. So, but what would we focus is on the hole transfer and the electron transfer. When the electrons always want to decrease their energy, so because of these bands or levels that are present here, that is in the conduction band of the semiconductor, the conduction band is higher, position is higher here, lower here. The electrons will try to decrease their energy and go in this manner, and it will be conducted via the wire to this electrode. Holes will always move up the energy level. Why is that? Because when the holes move up, hole is a lack of an electron, the energy, the electrons are moving down. That's why we say that holes are moving up. So why do we need to compare the energy levels of a semiconductor with the energy levels of redox pairs? Because we are always talking about electron transfer between the electrode and the electrolyte. When a hole transfer occurs from a semiconductor to the electrolyte, electron transfer is occurring from some redox species that is present in the electrolyte to the semiconductor, right? To know in which direction electron transfer and hole transfer will take place, we need a way to compare the position of the energy levels in a semiconductor with the positions of redox levels. Okay, so to facilitate electron transfer between semiconductor and redox species, we need a common scale wherein the energy of the redox levels that are typically mentioned in electrochemistry can be compared to the energy levels of a semiconductor. We'll again elaborate this as we go further. So moving on, we have to also specify a few other things. So when we say there is a band gap of a semiconductor, we can, let's say, band gap of cadmium selenide. So we can think about the frequency of the photon, that the minimal frequency of the photon that is required for an whole electron excitation in a semiconductor, right? So that frequency would be this number. This probably you've seen this in your high school. It's better to think through this using wavelengths. Again, these are some things that you must have seen in your high school itself, right? In the next lecture, we will look at a very important concept that is present in the semiconductor electrolyte interface, that is called band bending. This band bending is crucial for separating an exciton. What is an exciton? We have already introduced this term. Exciton means it's an electron hole pair. These have to be separated so that you can do some chemistry with the holes as well as do some chemistry with the electrons. To make that separation possible, this bands that are present in the semiconductor have to be bent. Okay, so we will elaborate this concept. This concept is called band bending. That will be done in the next lecture. Thank you.